Let's try another problem. Here is sample calculation B. We have nitrogen and hydrogen gases mixed in a 2-liter closed container reacting to form ammonia, NH3, in an equilibrium mixture described by the following reaction equation. We have N2 plus 3H2 yields 2NH3. What we want to do here is find the value of the equilibrium constant, K sub C, and that means we'll be expressing these in terms of molar concentration to begin with. We'll want to find the equilibrium constant K sub P if the amounts present of the reactants and products are as follows. We'll have 0.20 moles of N2 in this 2-liter container, 0.050 moles of H2 in this 2-liter container, and 0.15 moles of ammonia. The temperature and pressure of the container are 298 Kelvin and 4.9 atmospheres of pressure. Our first step in solving this is to find the molarity of each of the reactants and products at equilibrium. So we need to take the number of moles of each gas and divide it by the volume of the container, which is 2 liters, which is what we do here. So the 0.20 moles of N2 divided by 2 liters gives us a concentration of 0.1 mole per liter nitrogen. 0.050 moles of hydrogen divided by 2 liters gives us 0.025 moles per liter of hydrogen. And finally, our ammonia is 0.15 moles of ammonia divided by 2 liters, which is 0.075 moles per liter of ammonia. Next, we'll write the equilibrium constant expression and plug in the molar concentration values to calculate K sub C. So here's our equilibrium constant expression, K sub C. It's equal to the concentration of the ammonia squared divided by the concentration of nitrogen times the concentration of hydrogen cubed. Remember, when you put a chemical formula inside brackets, it represents moles per liter or molar concentration. And we continue that out and substitute the numbers in. So we have our 0.075 moles per liter of ammonia squared divided by the product of the 0.10 moles per liter of nitrogen times the 0.025 moles per liter cubed. Our K sub C value then is 3600. Please note that we do not express units in an equilibrium constant expression. It is a unitless quantity. There is a long, very involved explanation as to why it's true, and it's best probably for you to save that explanation till you get to physical chemistry at the college level. Continuing with the solution to sample calculation B, we want to find K sub P, which is the equilibrium constant expressed in terms of pressure rather than in terms of molar concentrations. There's a wonderful mathematical relationship that simplifies this for us, and it's this: K sub P is equal to K sub C times the product of RT raised to a power of delta N. Now R is the universal gas constant, 0.082 liters times atmospheres over mole times Kelvin. T represents the temperature in Kelvin. Delta N is equal to the moles of gaseous products minus the moles of gaseous reactants. You do not use the experimental values here. You simply use the coefficients from the balanced equation. So delta N is the difference in the moles of gaseous products minus the moles of gaseous reactants based on the stoichiometric coefficients from the balanced equation. We're going to go ahead and finish this calculation by putting Kp equal to our equilibrium constant expression in terms of molar concentrations, and that K sub C value is 3600 times the product of 0.082 liters times atmospheres over mole times Kelvin times 298 Kelvin raised to a power of -2. Now this is raised to the power of -2 because on the product side of this balanced equation we have 2 moles of gas. On the reactant side, when we add the coefficients, it would be 1 plus 3, which is equal to 4. So delta N here would be 2 minus 4, which yields -2, which is the power that will raise RT 2. So K sub P here is equal to 6. So be very aware when you use this equation to make sure when you calculate delta N, it's the sum of the stoichiometric coefficients from the balanced equation of gaseous products minus the sum of the stoichiometric coefficients from the balanced equation of the gaseous reactants. Let's try another sample problem here, sample calculation C. We're going to take this reaction and reverse it. So we have gaseous ammonia is introduced into a 4-liter evacuated container. Now, when you read evacuated container, what that means is that the container is a vacuum. There's no gas present in it before we introduce the ammonia. The temperature of this container is 305 Kelvin, and once the ammonia is introduced, it will begin to decompose into nitrogen and hydrogen gases, and it forms an equilibrium system according to the reaction that you see. 2NH3 yields N2 plus 3H2. At equilibrium, the pressure of each gas is the partial pressure of NH3 is 0.75 atmospheres, the pressure of nitrogen is 0.40 atmospheres, and the pressure of hydrogen is 1.2 atmospheres. So the goal of this problem is to calculate K sub P and K sub C for this system. First, we're going to write the K sub P equilibrium expression and then substitute the pressure values and solve for K sub P. So K sub P is equal to the product of the partial pressures of nitrogen gas times the partial pressure cubed of hydrogen gas divided by the partial pressure of ammonia gas. So it's 0.4 atmospheres times 1.2 atmospheres cubed divided by 0.75 atmospheres squared. And so K sub P is 1.2. Now that we know K sub P, we can go ahead and calculate for K sub C. We use that base equation that K sub P is equal to K sub C times the product of RT raised to a power of delta N. In this case, our delta N is going to be the stoichiometric coefficient sum of the products, which is 4, minus the stoichiometric sum of the reactants, that are gases, which is 2. So 4 minus 2 is 2. Our temperature is 305 Kelvin, and our R value is 0.082 liters times atmospheres over mole times Kelvin. We're going to take that equation and rearrange it to solve for K sub C. It will be equal to K sub P divided by RT raised to delta N. So our 1.2 divided by the product of 0.082 times, liters times atmospheres over mole times Kelvin times 305 Kelvin squared. And when we calculate that out, we get 0.0019 for our K sub C value. This is the end of part 1-2 of the Equilibrium video podcast series. I want to leave you with another quote from Mark Halperin, a world-famous novelist. All rivers run full to the sea. Those who are apart are brought together. The lost ones are redeemed. The dead come back to life. The perfectly blue days that have begun and ended in golden dimness continue, immobile and accessible. And when all is perceived in such a way as to obviate time, justice becomes apparent, not as something that will be, but something that is. Stay tuned for part 1-3.